In this video, we will do a solved example which will help us understand how Taylor series approximations work and how they are applied to the world of finance. We won't be really doing a formal proof of Taylor series approximations, but rather we'll be going through this stepwise solved example which will help us rationalize how Taylor series approximations are arrived at, so that we don't have to memorize anything. Okay, we are given that there is a zero coupon bond. Its face value is $100. Its original maturity as of the time point at which it was issued was 30 years, and we are given that the continuously compounded yield is 5% per annum. Okay, so to value this zero coupon bond, let's draw a simple cash flow diagram. So since it's a zero coupon bond, there are no intermediate cash flows involved. There are no coupons to be worried about. There is this single cash flow which corresponds to the face value of this zero coupon bond that is handed out to the investor of this bond when we reach the stated maturity, which is 30 years. Okay, so a single cash flow at this time point t equal to 30 years, and this cash flow is of $100, which is the face value of this zero coupon bond. Okay, now to find the fair value of this zero coupon bond, the first thing which you have to do is to pick which point in time would you be placing yourself at. If, let's say, you were to place yourself at this point, which is t equal to 0, let this be the time at which the zero coupon bond was issued, then the fair value of this bond as of this time point is very simply $100 discounted to this point in time, which is basically 100 multiplied by the corresponding and the appropriate discount factor. Okay, so 100 times e to the power minus 0.05, because 5% is my relevant interest rate or discount rate, and because it is continuously compounded, therefore e to the power minus 0.05, that times the residual maturity of this bond as of this time point, which we know is 30 years. Okay, if you were to plug these numbers into your calculator, you can check that the fair value of this zero coupon bond comes out to 22.3130. If now you were to move yourself and position yourself as of this time point, which is the maturity of the zero coupon bond, the fair value of this zero coupon bond should be nothing else but the face value, which is $100. So what does it tell us? It tells us that depending on where we position ourselves on this horizontal axis, which basically denotes the time, the value of the bond is different. See, it's 22.3130 here, it's $100 here. So what I can do is that I can position myself at some point t, which is, let's say, anywhere between 0 and 30. Okay, and I can write down the value of my zero coupon bond as a function of this time point at which I am placing myself. Okay, so taking a clue from this expression, I can write down the fair value of my bond at any t to be simply equal to the $100 discounted by multiplying with e to the power minus 0.05 like this times the residual life of this bond when I position myself at this time. The residual life is 30 minus t, these many years. Okay, so 30 minus t, right? So this is the value of my bond at any t, essentially a function of t. Okay, so while we are at it, let's very quickly differentiate this guy and arrive at the first order and the second order derivative with respect to t. A very simple differentiation. All you need to do is very quickly apply the chain rule. Okay, because it's e to the power some function of t. Okay, this guy is some function of t. So when you differentiate this guy once, this is what you get. This is the first derivative of f with respect to t. You can pause this video and very quickly confirm that this indeed is correct. It's a simple application of chain rule. Okay, if you were to differentiate it once more, I mean this guy, with respect to t, you will get the second derivative, which is this guy. Okay, so let's do this. Let's quickly consolidate what all information we have at the moment. We have f as a function of t. This is how it looks like. We have plotted f as a function of t in this plot. We have the formulas for the first order derivative and the second order derivative of f with respect to t. Okay, now the first part of this question, part A, wants us to position ourselves at t equal to 16, which means that 16 years have passed since this zero coupon bond was first issued. Okay, so by placing ourselves at t equal to 16, let's very quickly, by substituting t equal to 16 into these three formulas, work out f at 16, the derivative at 16, and the second derivative at 16. Okay, so you can quickly check using your calculator that these values, they come out to 49.6585. This guy is 2.4829 and this guy is 0.12415. Okay, please do check these numbers. Don't really believe my calculations. Okay, then let's move on to part B of this question. So in part B, what we've done is that we have moved time a little forward. Okay, we were positioning ourselves at t equal to 16. We have moved time forward by 6 months. In years, 6 months is 0.5. Okay, so that means we are now positioning ourselves at t equal to 16.5, or maybe we are assuming what will happen, or we are trying to find out what will happen if we were to move ourselves to t equal to 16.5. Okay, so what is of interest to us is to find the value of our ZCB, zero coupon bond, at 16.5. Well, it's a simple task. So if you substitute 16.5 into ft, which is this guy, quickly check that f at 16.5, it comes to 50.9156. But the question asks us to work out a linear approximation to this guy. Okay, why are we concerned about working out an approximation when we can work out the accurate value of f at 16.5? The reason that we are looking for an approximation is because when we talk about practical use cases in the world of finance, many a times recalculating a given function at a changed value of this independent variable, in this case it's time, it's not always feasible. Okay, many a times calculating functions is computationally quite intensive. Okay, so many a times what we do is that we try and approximate the value of a function based on information which is available to us at a nearby point. So in this case, remember, we have already captured a lot of information at a nearby point. Okay, and this nearby point is t equal to 16. And we are asking this question, can we use this information at t equal to 16 to approximate f at 16.5? Okay, and in part B of this question, we are seeking a linear approximation. Linear means straight line. Okay, so for this purpose, first of all, recall what is the equation of a straight line? Usually we remember the equation of a straight line to be y is equal to mx plus c. Now in this case, our independent variable is not really x, it's actually time. So let's write it as y is equal to mt plus c. It's a straight line with slope m and with intercept c. Okay, so what I have done here in this plot is that I have clearly marked the point at which we have recorded our information. Okay, this yellow point corresponds to t equal to 16. Think of this point to be the anchor point around which we will build our approximation. Okay, now when we worked out f at 16.5, what did we do? We positioned ourselves at this yellow point and we walked a little to the right along this blue solid curve. And we are saying that in the practical context, walking along this blue curve, which is the actual plot of our function f, may not be feasible. And therefore, as an approximation, let's do this. Let's switch to walking along a function which is very simple to evaluate, and nothing can be more simple than to evaluate a linear function. Okay, so we are saying that to approximately work out f at 16.5, let's not walk along the blue curve, the blue plot, let's walk along the dotted straight line. And this figure tells us that this dotted straight line is actually the tangent to the blue plot at this anchor point, which is this yellow point. Okay, t equal to 16. So what needs to be done? Essentially, we need to calculate the equation of this dotted straight line, the equation of the tangent. Now let's do this. To find the equation of this tangent, let's approach it in a slightly different way, in a way which will make our lives easy as far as part C of this question is concerned. Okay? To understand what I'm about to do, just look at the aim which we have in mind. Our aim is to switch from walking along the blue plot to walking along the straight line. Walking along this straight line would make sense if this straight line satisfies a couple of conditions as of this point, which is the yellow point. Okay, and these conditions are, number one, this straight line should be such that the value of the function as read from the blue plot, which I know is f at 16, I've already worked out this value, exactly matches the value which comes from this dotted line. At least things should match as far as this yellow point is concerned. They might diverge in this region or this region, but at least let's aim for an exact match at this point. Okay, this is my first condition. F at 16, which is this guy, should be exactly equal the number which I get, equal to the number which I get by plugging in 16 into this guy. So this should be equal to m, this times 16 plus c, my first equation. My second equation is that the slope of this blue plot at this yellow point should exactly be equal to the slope of this dotted straight line. And the slope I know is m. So this is my second equation. See, f prime at 16, I've already worked it out, should be equal to m. Two equations, two unknowns. Let's quickly solve for the m and the c. M is this guy. Substitute in this equation. You get c to be equal to 9.9321. Okay. So what do we have now? We have the equation of this straight line, and we are saying that in the vicinity of this yellow point, f at t, f as a function of t is approximately the same as 2.4829t plus 9.9321. Okay, this is my linear approximation for f of t in the vicinity of t equal to 16, which is my, if you remember, anchor point. Okay, so very quickly what I can do now is substitute in the right hand side t equal to 16.5 and get an approximate value of f at 16.5. Please do this substitution and please confirm that what you get is 50.8995. Okay, the actual value of f at 16.5 was 50.9156. Pretty close. Okay, not that bad. Now please note that this linear approximation, visually it is telling me, this plot is telling me that it is a good enough approximation if I limit myself to, let's say, this region. That means I do not move too much to the left or too much to the right of my anchor point t equal to 16. Okay, within this region, the straight line and the blue plot, they kind of overlap each other. Okay, so please do remember this, that linear approximations, they work out quite well if the perturbation from the anchor point is not that much, and number two, if the non-linearity of your original function, I mean the curvature of the original function, is not that much. Now, this plot is also telling us that my linear approximation becomes a bad approximation when I reach this region and when I reach this region. That means when I walk too far away from my anchor point. To make my approximation still good enough, let me move from a linear approximation to a quadratic approximation. Okay, an approximation which includes t square. Okay, so that's what we will do now in part C of this question. So in part C, we are saying that let ft in the vicinity of t equal to 16 be approximated by a quadratic function of t. How do you write a quadratic function in general? You write it as at square plus bt plus c. Let's do this. Let's very quickly differentiate this guy once to arrive at the first order derivative, and then once again to arrive at the second order derivative, because we will need these two derivatives. Differentiating it once gives me a times 2t plus b times 1 plus a 0. This is the first order derivative of this guy. The second order derivative would be differentiate this guy with respect to t and you get 2a. Okay, if you remember the approach which we followed in part B of this question, a similar approach would work here also. To make sure that my quadratic approximation is good enough, using the anchor point and the information available at this anchor point of t equal to 16, I need to impose three conditions. The value of the function should match between the original function and the approximation at t equal to 16. The first order derivative should match between the original function and the approximation at t equal to 16. And now in this quadratic approximation case, even the second derivative should match, okay, at t equal to 16 between the original function and the approximation. Okay, very quickly, let's do this. F at 16 is this guy. I want it to be equal to a times, substitute 16 here, 16 squared plus b times 16 plus c, equation 1. This guy should be equal to, substitute 16 here, a times 32 plus b. This guy should be equal to this guy, 2a. Okay, so a can be found out from this equation. Substitute in this equation, calculate b. Substitute a and b into this equation, calculate c. What you will find is that the values of a, b and c, they come out to be respectively 0.062075, that's a, so a times t squared, plus b comes out to 0.49666, okay, that times t, plus c, it comes out to 25.82202. Okay, so this is my quadratic approximation for my original function. Very quickly, substitute t equal to 16.5, pick up your calculators and please calculate what you get as this right hand side expression. What you will see is that f at 16.5 now comes out to 50.9168. See, it's now even closer to the actual value 50.9156. Okay, and this is the plot of our quadratic approximation. See this dashed plot. It very closely overlaps as much as possible with our solid plot, even if the perturbations from our anchor point are large enough. Now, coming back to the focus, the aim of this video, which was Taylor series approximations, let's do this. Let's very quickly write down our quadratic approximation. Okay, this is our quadratic approximation. AT square plus BT plus C. To understand Taylor series approximations, let's change our variable. Okay, because we are talking about an anchor point which is 16, let's write down t in the vicinity of 16 to be very simply t is equal to 16 plus the deviation from 16. Okay, so I can express t in the neighborhood of 16 to be t is equal to 16 plus a deviation, let's call it delta t. So let's do a change of variable. In this approximation, replace t by 16 plus delta t. That's what I have done here. Okay, let's open up and simplify. So this guy times 16 squared plus this guy times 16 plus this guy. Quickly check, it will be the same as f evaluated at 16. Okay, then plus, let's take a look at the delta t squared term. There's only one term which comes from this guy. Okay, so this times delta t squared. What is this guy? Quickly, this guy is half of the second derivative of f of t evaluated at t equal to 16. Remember the value? It was 0.12 something, right? And this is the half of that. Plus, actually this times delta t squared plus, don't forget there's a delta t term which comes from here and this delta t term sitting here. Okay, so the coefficient of delta t term will be this times 2 times 16 plus this guy. Okay, you can check that this, the coefficient of delta t, it comes out to be, please do this check, it comes out to be 2.4829, which if you remember is the first derivative of f with respect to t evaluated at 16. Okay, this way of writing our quadratic approximation is much more intuitive and it's much more representative of what we need to establish in the end, Taylor series approximations. Now, next step, let's do this. There is nothing special about 16. Let's denote 16 in general by an anchor point t naught, some value of t which is t naught. So I can write down this guy to be ft is, I should actually always say approximately. Okay, so here also approximately. Here also ft is approximately f at t naught. Remember, I am replacing 16 with a generic t naught. Plus, let me write this guy now, f prime at t naught, this times delta t plus, take a look at this guy, half f double prime at t naught, this times delta t the whole squared. Okay, this is Taylor series approximation of my original function f of t around this anchor point t naught and including terms up to and including the second order derivative. It's a second order Taylor series approximation of f in the vicinity of t naught. Okay, now This is my end result which we wanted to establish. Please note that in the world of finance, usually we either stop here, so that would be a first order Taylor series approximation, or we stop here. That means a second order Taylor series approximation. Nobody is stopping you from actually keep moving to whatever extent, to whatever order you want to move to. Okay, that means if I want to include a third order term, take a look at the pattern which you can detect from these terms and write down how the third order term would look like. It will have the third order derivative of f with respect to t evaluated at t naught. It will have delta t, which is t minus t naught the whole cube, and please note we have been writing this guy as 2, but in the Taylor series expansion this is actually 2 factorial. Therefore the pattern tells me that here you should have 3 factorial. Okay, so this is how a Taylor series expansion looks like, in which we don't stop, we keep going till infinity. When we talk about Taylor series approximation, we do cut off this expansion at a point where we feel that we've captured enough. We can stop here, a first order approximation, we can stop here, a second order approximation, stop here would mean a third order approximation, and so on. So please note this is the difference between Taylor series expansion, which never stops, and Taylor series approximation, which is cut off at some point. Okay, this video was about understanding the rationale of how we arrive at Taylor series expansions. Okay, so that you don't have to memorize why this particular expansion looks the way it does.